I'm Ted Weatherford. I'm VP of Business Development. I've joined with John, who's our distinguished engineer and architect on our E-Series products.
Nice to be here.
Yeah, and I'm going to cover the X-Series products now. The X-Series product is a Ethernet switch, and what distinguishes it from all the other Ethernet switches, literally, is that it's programmable. And its programming model is a load store type model. You have 3,072 little Harvard architecture cores inside this Ethernet switch chip. All the competition is approaching the problem with a fixed pipeline. They may call it programmable, but at the end of the day, it's a fixed VLIW pipeline with fixed elements and programmable elements, and it has a fixed latency, and you don't have the flexibility to do tasks in parallel. What we've done is a run to complete model with this 3,072 little Harvard architecture cores, and it gives us two things. It gives us more flexible than any Ethernet switch chip that's available or has ever been designed, with an actual architecture I'm showing here that allows us to scale down or up really gracefully. To call it an FPGA, because it kind of looks like an FPGA floor plan, would be a complete misnomer, but it is symmetric. And if you look at all the little squares, there's 64 of them. And each of those 64 squares has 48 processors, okay? And they're run to complete. So when you go to program this, you're not forced into a pipeline, okay, of sequential steps where you write the code, you turn the code 90 degrees and you drop it into the pipeline. You literally can do recursion. You can do whatever you do within your instruction space and the time you have for the minimum packet size. We've sized all the caches. We've sized all the clocking so that you have this amazing low power device with tons and tons of header processing. You can do 11 layers of MPLS, for instance. So all kinds of IP inside IP, any kind of encapsulation, whether it's already a standard or something that's developed. And I'm gonna, yeah, thank you.
Ultra Ethernet, things like that. These sorts of things that are starting to come out of the woodwork. UA Link, I'm guessing that's UA Link here, but how does that play in this space?
It's exactly where this shines. And for Ultra Ethernet or ESON or some of the Ethernet-centric extension protocols that are coming out for AI, we're there. We can ship this. And some of the physical layer mechanisms, like the layer 2 retries, there's things in there that we didn't catch with this particular tape out, but protocol-wise, congestion management-wise, the in-flight packets for the servo loops, for all your congestion management, all that's dialed in and completely flexible. You can build your own server for any scheme. So it's ready for that, better than all the other products because they're fixed in function. And that was the one exception, is the retry. And then on the UA Link reference, this is not a UA Link switch. That's correct. It's not. I'll just offer the latency of this switch while we're at it. A UA Link is a very low latency switch. It's back-end scale-up centric. This is a front-end scale-out or a back-end scale-out a product. And we can get down to 450 nanoseconds, which is screaming for a traditional scale-out switch. I mean, your Broadcoms are at 800 when you really measure them. So one of the advantages of having a run-to-complete architecture is you can dial in the latency to be as good as it gets.
So Ted and Jack Poller with Paradigm Technica, can you talk a little bit more about run to complete and what that means for you?
Yeah, thank you. So there's really three different architectures. There's a von Neumann, a Harvard, and of Dataflow. And run to complete speaks to an architecture where you have an instruction set that you're running, right? And you'll run till you complete the overall operation of the packet frame coming and being modified and being sent out. So the frame shows up, Ethernet, it gets modified, it gets shipped on its way. And what run to complete allows you to do is have complete flexibility. You don't have to handle the packet one piece at a time sequentially. You can move around to anywhere in that packet header or that packet within a window. So the run to complete is a amount of time or clock cycles you have to do work, but that work does not have to be only sequentially. That's my level of understanding. Yeah, it's more flexibility and it allows you to do things in parallel. And there are many packet operations that can be done in parallel. So you end up saving time and getting latency from it. and not being caught off guard if protocols change or you have something interesting. Where it really matters, because all of us use standards, right? It matters with all of the instrumentation and telemetry. The observation and the troubleshooting of these networks is getting increasingly complex. And this kind of model just allows you to build the best instrumentation and telemetry with really less constraints. So it's symmetric and it'll scale either way. So each one of those blocks is a 400 gig block. So if I want to go build a 400 gig, a tiny little switch, I just do one block. If I want to scale up to 400 terabit, and I shouldn't have said that number, then you increase the block size. So it does have that sort of geometric scaling up and down in this graceful, symmetric way, which you won't see when you look inside the fixed function data center switches. You'll see pipelines, and they're fixed in nature, and there's a number of them. I'm not going to cover this. It's an eye chart, but I want to point out that we have large amount of packet buffer. We're very low power. We sell the 12.8T in derivatives. It's the same die, but we downclock it. You can turn the SerDes down. The SerDes can be all different speeds. So we're software defined even at the physical layer. You can have SerDes coming in at 100 and going out at 25 with different modulation schemes. You can mix and match. And this is actually really, really, really sexy because you've got these new fabrics up there with 100 gig SerDes that have just been deployed last summer, and they'll be around for a while. And then downward, you've got all the legacy. So you can run it 10 gig, 25 gig, 50 gig, 100 gig, 200 gig with whatever SerDes and whatever modulations you want. So it really gives you this building block for looking backward as well as forward. People ask us, why do we only do 12.8? It's because we're going after the edge, and I'll cover that later. We're going after half rack, full rack, 2 rack. We're going after satellites. We're going after base stations, okay? The performance is there. The chips are here. The boxes are out by our Taiwanese friends, Acton and EdgeCore. You can just measure everything, but you got to show people some performance if you're claiming to be programmable and lower power than a Broadcom or an NVIDIA or a Cisco or a Marvell. So we do that. And that's what this is. It's the watts on the left, and it's breaking down the SerDes, the core, and it's showing what your max and mins are over that. And this is crazy to have a 12.8T switch that's programmable at under 200 watts. It's disruptive. This is showing you efficiency of the most important thing about a switch besides its radix. Switches are connectivity at the end of the day, and how much bandwidth and how many different connection points or ports you can have. But the other thing that matters, and it really matters, is the shared memory or not buffer, the frame buffer. The packets come in, and do they come in fair? And can you utilize, in times of burstiness, can you utilize the whole buffer that you paid for without overrunning it? So in our example here, we take 127 ports running it at 100 gig each, and we ram it out 100 gig port, and we find out how long till the packet buffer fills up does it overrun. And then we do it, at the different oversubscription rates and different packet sizes, and we show that the utilization never drops below like 86 or something. And in real world tests, that's amazing, okay? So if you're a switch head like I am, then you're like, oh, wow, that's amazing. The Tomahawk products that are dominating the market.
Ted?
Yeah.
Ray Lucchese, Silver Nickel.
Oh,
Still trying to get a handle on this. You're not actually manufacturing DPUs. You're actually manufacturing the chips that would go into DPUs or chips that would go into a switch.
We have 2 products. They're both chip products. I'm covering the switch first. It's a separate tape out, and it's just an Ethernet switch chip with 128 100 gig SerDes on it. It's a switch chip. Next, we're going to cover our ESERs, which is a DPU. So we have 2 products. It is amazing. 200 engineers doing 2 products of this complexity it's a lot. So we have 2 chips. They go together nicely. They have the same SerDes IP. They play really well together because the highest volume opportunity is the top rack and the front end interface or the back end interface into the server or the GPU server. And so we bookend that with these 2 products, especially for the edge. We're a chip company, 2 chips. I'm going to pick up the pace a little bit. This is showing the fixed pipeline and the map pipeline approach, which is not ours, against this run to complete full SDN. We can imitate the other architectural approaches. They can't imitate us. So we can make the trade-offs between latency or the amount of work you're doing and the amount of power you're spending. So this is more of a deep dive for somebody that wants to compare these products to data flow architectures or fixed function stuff. But suffice it to say, we're trying to say that you can have multiple pipelines, you can have branches, you can have a physical connection and a logical connection that's flexible.
Challenge with something
Yeah.
like this in the past has been latency. I mean, to do something that's not pipeline or not map pipeline and achieve the line speeds has always been impossible before.
We're proud of it. Yeah. I'll give you a clue. If you're designing for your worst case and you're building a pipeline, you've got a lot of stages you don't need. If you build with us and you put our 3,000 processors in a line, if you want to pretend it's a pipeline, you can, and you'll just have less instructions, or you could have one processor handle a whole packet. You can build a pipeline like they do, or you can have one processor handle one flow. You have this whole range.
I guess the question is, what's the clock speed, and how fast are you able to maintain line speed across however 128 ports? I guess.
Yeah, it's 128 ports at 128 byte minimum packet all day long till the cows come home, with a maximum power of 186 watts at 12.8. It's mind bending, and I can just say that the team is basically on their 8th or 9th generation network processor or switch when you combine the people. We have people from Motorola, Freescale, NVIDIA, Broadcom, Juniper, Cisco. It's a pretty senior, strong team that's been doing network processing, DPUs, and switches for, 30 plus years. Yeah. No, it is, before we had the products, it can be a lot more interesting debate. Now we just have the products. So you can just put them on the test and test. In fact, we have built-in self-tests that we don't advertise, but that's a really nice feature we have too. You can run 12.8 terabit of line rate. Every port has its built-in Xsight tester. So you can even test the device in its own printed circuit board without an expensive $3 million tester. So programming model is always the challenge for programmable products. We have an assembler that we've wrapped in Python, and we provide libraries. You've got to configure the tables for forwarding, the tables for security, the tables for quality of service, the meters, the counters. You have to set all that up, and they're structures, and we have libraries, and you have to program this thing in our assembler. However, we opened up the instruction set, and our first customer, which we did a PR on, called Xsight, they're a local cloud guys, you know them?
In the field,
They wrote a P4 compiler on it. So this is a simple RISC instruction set. I shouldn't call it RISC. It's technically a Harvard architecture, but it's a small little instruction set that you'll be familiar with if you're a programmer, especially somebody that really programs deep. And they just wrote a compiler on top of it. So our whole ethos is it's open, do what you want. And we also have plans of putting out a P4 compiler early next year also, because we have a lot of customers that really want that higher level, or what I would call fourth generation language. It's kind of dated terminology, but so today we give you courses. We've got all the examples, and we haven't had a customer we had to write all the code for. They've all taken the classes and written the code and done quite well. And one of them is, I'll foreshadow, is SpaceX. So we're really excited about that. The architecture and the normal stack of what you target to, on the very bottom, I'll start there. You've got the switch device. That's what you really care about. But you can also do simulators, and you can also do hardware emulators. We built our own hardware emulator. We have a room full of FPGAs of design we did ourselves. We do all our own hardware emulation. We don't buy hardware emulators. We have our eval boards, which are just rack systems, pizza boxes with front panel ports like you'd see in a top of rack switch or a fabric. And then this just shows the network operating system down and what we provide. And we put all this, on open. Anybody can get to it. And the network operating system of choice for all of us now is Sonic. And we do our own Sonic distribution. And then we have 2 partners that provide hardened Sonic as well. So that's what your normal stack looks like. And this is what a box looks like. I have it right over here. I just want to say it's real, it's available. This particular one is what we call the universal switch, because the MPA connectors are QSFPs and you can put whatever you want in them. Each little rectangle is 4 SERDES, and those SERDES can run at whatever speed you want. And there's common media for 4x25, 4x50, 2x50, et cetera, so that you can build a top of rack here, which we call a top of rack upgrade or a TOR upgrade, so that, again, you can connect to any kind of speed up and any kind of speed down. You can migrate from older network interfaces to newer ones, or maybe one storage box has a certain kind of thing and it's in the same rack with a server or a GPU server.
Got a question.
Yeah.
Specifically about the Tor here. Do you think, and you can theorize here a little bit, do you think once 224 SerDes comes around, you'll be able to stick with the same form factor, low power, and not go liquid cooling?
Depends straight up on how much bandwidth you want.
Straight on bandwidth.
If you did a 25.6T, you could stick with this.
Yeah.
A 51.2T would be harder.
Yeah.
It'd be harder. That I'd have to defer to a switch expert. But that's the answer.
Okay. No, that's-
yeah, the answer.
maybe 51 too, but
Yeah.
but
And our architecture is really on par at a geometry level with the others. So if we do a 100 terabit switch,
right.
it's gonna be 1,000 watts.
Yep.
So what we've done to just be so disruptive on power now, full disclosure, is we went to 5 nanometer when everybody else
We're
was
still in the old days. Yeah.
was going forward with very large rating switches, and we did it to capture the edge, the economics of the edge, the power of the edge, and the right amount of connectivity for the edge. I got an example on that coming. I'm going to just move faster. We built this for a large hyperscale for this exact thing. Their particular format is just a different cage. This is a 16 by 800. So that's the Tor they happen to use. And this gives them a benefit of half the power, half the rack space, a quarter of the cost.
That product was GA24.
Yeah.
So how long has this puppy been out there?
We first sampled this April of 2024, and we called it generally available. Both our products have been first spin, no metal spins to market. We called it generally available in November of 2024, and it's been in mass production since summer of 25. Yeah. No, this is out there.